imagine it has some screws there, doesn't let it move, and it can move in this direction. So what's going to happen to the vertical stress if I decrease the temperature? Let me make this thing a little bit more realistic so you can picture that in your mind. Here you have some rollers, okay? Those rollers do not let the rock to move in direction 1, but it can move in direction 2. And the rollers are attached to some sort of rail here on the side. So the rock cannot move in this direction, it just can move in this one. I lower the temperature. What is going to happen with the stress?
Put the stress tensor to put in some.
Okay, let's do the following. Let's measure stress as a function of time. And let's say that the vertical stress was this at the beginning, and the horizontal stress was that. What do you think is going to happen with the vertical stress as I lower the temperature? No. Well, why would it increase? Well, it can move in the vertical direction. So if you lower the temperature, the rock will tend to decrease in size, right? And if it decreases in size but still has the same stress, Mr. Awan.
I was just going to say that the stress is going to remain constant because the forces are the same.
The forces are going to be the same, and probably the rock will change in size in this direction, but not in the other direction. So sigma v will stay constant if I lower the temperature. And look, actually here we could also plot this as negative delta T, right? So I'm decreasing the temperature in this direction. But what's going to happen to the horizontal stress? Now the rock is going to try to shrink, right? But it can't. So, Mr. Boswell, what did you say?
It's going to increase.
Increase the stress.
Yeah.
So remember that we call compression positive. So the more compression, the more positive. The less compression, the more negative.
Mm-hmm.
So it's going to get more positive or more negative? Or less positive?
Kind of confused me there. But I think that it's going to push on the outsides on the roller.
It's going to push or it's going to pull? We're lowering the temperature.
I think it's going to have an opposite effect because when we're pushing it,
Yeah.
it's going, due to the Poisson's ratio,
Yeah.
it's going to have
Yeah.
an opposite direction force, and then
Yeah.
when we're contracting it, it's going to be going the other way. So it's
Okay.
kind of going to cancel out a little bit.
Okay, well here we're not pushing. The sigma v is constant. But we're pushing, but that's already taken into account.
Oh, okay.
That's why we start at some non-negative stress. So, Mr. Boswell, you. So there are three options, okay? This one could, let's say, increase, could stay the same, could decrease. So option number 1, raise your hand if you think that's a solution. Option number 2, no. Option number 3. I see most of the people with option number 3, and actually that's what's going to happen. The horizontal stress is going to decrease. And you may think this as a silly example, but this is exactly what goes on when you inject into a formation with a wellbore that has a cold fluid. So if you're injecting with the cold fluid, what you cause is a decrease on the effective stresses, and you may favor fracturing due to the lowering of temperature in the formation. It's the same thing. So all of these changes of temperature, they're going to bring along what are called thermal stresses, and you can solve all these kind of problems with the theory of thermo-elasticity. So we say multi-physics problems. That's why they are called multi-physics, because they bring other physical phenomena into what we already know about stress and strain. Another type of loading that we have already seen, but not with the best solution so far, is when you have changes of pore pressure. So when you have changes of pore pressure, we usually refer that instead of talking about instead about talking about total stresses, we work with effective stresses. And actually there is a name for that in order to be more rigorous. This guy, Terzaghi, came up with this law in order to calculate effective stress, in which effective stress is equal to total stress minus pore pressure. But it turns out that when you consider the formation of the rock too, of the solid minerals, this is not very accurate. And instead of that, there is something which is called Biot's effective stress, in which the effective stress is the total stress minus a coefficient which is called the Biot coefficient, which is equal or less than 1. And with that, you can solve problems of deformation as a function of changes in pore pressure accurately. And that, so this one is called thermo-elasticity. If you were to use this type of relationship, that's something which is called poro-elasticity. And if you go through my notes, you will see there a little bit more the equations. They are not too different. Usually, if you assume alpha equal to 1, for most problems, you're going to be fine. So let's not worry much about that. There are some other very important things that we have to cover. So we'll not go through the theory of poro-elasticity. Thermo-elasticity we're going to see later on when we talk about wellbore failure. Because as you may imagine, also if you're dealing with a cold fluid, that's going to favor rock shrinkage around the wellbore, and that's going to favor tensile stress. And the last type of loading that we're going to talk about, it's about changes in, any idea what that could be? No, this is not viscosity. We never talked about, but remember, this is not viscosity. This is something related to chemistry, and it's called a change in the chemical potential. So basically now we're adding some chemistry to the rock. So for example, if you have a rock made out of salt or a rock made out of gypsum, and if you flow water through that, the strength of that rock is going to change dramatically. If you have a shale which is sensitive to the chemistry of the pore water, you can have what are called, so for example, here there are several things that can happen. The first one, we can have mineral dissolution and precipitation that are going to change precipitation, that are going to change what is the strength of the rock. We can have in shales, they are sensitive to the chemistry of the fluid, and we can have what is called a swelling stress. You guys have taken drilling, right? You remember what happens with shales? What type of fluids you use with shales in order to avoid the shale breaking around the wellbore? Water-based muds, right? So some types of these shales, just to make it put it in plain language, they don't like pure water or low salinity water. So if you were to drill with a drilling mud with low salinity, the shale would swell. And that swelling would make the rock fail. We're going to come back to this when we talk about wellbore stability, but just remember that many shales are sensitive to the chemistry of the water. So you either change the chemistry of the water, you add more salts, or you change the fluid directly. And instead of drilling with an aqueous solution, you drill with a oil-based solution. And there are some others, but we're not going to discuss those. But remember that in addition to strains, you can also change, or you can cause stresses by changing temperature, by changing the pore pressure, and by changing the properties of the rock, or changing the pore chemistry of the pore fluid. Changing the pore chemistry of the pore fluid is going to make some clays unhappy and swell, and it may also dissolve cements from the rock itself. They're going to change its strength. All right, so let's see how we're doing with time. We have half an hour more. So with this, we are done with chapter number 3, I believe, which is about elasticity problems in rocks. Okay? So today we saw that there is more than linear elasticity, there is anisotropy, there is viscoelasticity, and there is elastoplasticity, and we also saw that we can change stresses by adding temperature, by changing pore pressure, and by changing the chemical potential in the porous rock. So if we go to the next chapter, we have already talked about failure of rocks. We have said that rocks can fail with tension, and that will give you the tensile strength of rocks that you measure in the lab with the Brazilian test. Remember, you can load a very good rock will resist about 1 or 2 longhorns in a rod of 1 inch. And we also talk about shear strength of rocks. And so remember, this tensile strength, there is also shear strength. And similarly to what we discussed with the elasticity, also the properties of the rock and the strength properties are anisotropic, and depending in the direction in which you load the rock. So let's make the same schematic, and this topic is called strength anisotropy. Same thing as we discussed before. If we have a sedimentary rock made out of layers with interfaces between those layers, sometimes you can see those layers, but sometimes you can't. You need a microscope to see the layering. But in sedimentary rocks, there are always there are layers. So similar to what we did before, but not talking about stiffness, but talking about strength, I could come to this rock and take a vertical plug, I could take a horizontal plug, and I could also come to here and take a plug at 45 degrees. What do you think is going to be the strength of these rocks? Which one is going to be stronger?